goal of this section is to understand the methodology when developing C, C++, and OpenCL kernels. We'll discuss how to optimize kernels, and the main areas we'll look at are interface optimizations, unrolling and pipelining logic inside the kernel, and memory optimizations, primarily optimizations related to on-chip memory inside the FPGA. The Vitis software platform supports kernels modeled in either C, C++, and OpenCL, or RTL, Verilog, VHDL, or System Verilog. This methodology guide applies to C, C++, and OpenCL kernels. RTL kernels are developed by hardware engineers in a different way. Designing the kernel involves structuring source code and applying compiler directives to create the desired kernel architecture to meet our performance requirements. Prior to beginning kernel development or starting the coding phase, the following key kernel requirements or targets should already have been determined for your system. A throughput goal, or how quickly data will be processed in your system. A latency goal, how quickly results will be available or how quickly your system will respond to an input. Data path widths, the number of processing engines, and available interface bandwidths. The kernel development methodology follows a throughput-driven approach and works from the outside in. This approach has two phases, as indicated in the diagram. The first phase is defining and implementing the macro architecture of the kernel. This involves defining the top-level functions and, in particular, specifying the desired function interfaces, coding the load, compute, and store functions, and defining the connections between functions. The second phase, involving coding and optimizing the microarchitecture of the kernel, would involve identifying loops for optimization. Generally, we want to unroll loops to implement them in parallel, which will improve latency and throughput. Pipelining is another complementary technique for improving performance and utilization of the hardware. Arrays may need to be partitioned or reshaped to optimize the data flow within the kernel. The process for optimizing kernels looks very similar to host code optimization. We'll run the same processes and generate the same reports. However, this time, as we are focusing on the hardware kernels, the focus will be on different areas and information in those reports. We'll assume we are starting from functionally correct code. As before, when modifying code, you may need to go back and verify functional correctness in software emulation. This step isn't shown here. After the functional verification, hardware emulation is run to generate profiling data. This time we'll focus on the implementation details in the kernel compilation reports, the profile summary, timeline trace, and device hardware transactions to understand the baseline performance estimate for the system. The aim is to determine the timing interval or the throughput, the latency, and the resource utilization of the kernels, such as how many LUTs, DSPs, and block RAMs are used in the design. The last step is building and running on an FPGA target like the Alveo accelerator card. We can then analyze the reports from the system compilation and the profiling data from application execution to see the actual performance and resource utilization from the hardware. The goal of kernel optimization is to create hardware kernels that can consume all the data as soon as it arrives at the kernel interfaces. The key metric is the initiation interval. You'll see this annotated as two capital I's, double I, in the kernel reports. This is the number of clock cycles before the kernel can accept new input data, and this is related to the throughput of the kernel. We typically want the throughput to be as high as possible, so ideally we want to achieve an II of 1, or as low as possible while maintaining a high clock speed. That is, the kernel can receive and process data on each clock cycle. Optimizing the initiation interval is generally achieved with techniques such as pipelining, loop unrolling, and array partitioning. We optimize the hardware design to meet the requirements of the data path. There are four main categories for kernel optimization. First, interface optimization relates to the function and kernel interfaces in your design. You need to consider how functions and kernels are connected, the type of interface you should use for each parameter, and the size or width of the interface. For example, if the kernel will connect to a 512-bit PCIe bus, the goal should be to match the width of the kernel interface to this bus. Inside the kernel, we want to be able to receive and send burst transactions or stream data through these interfaces. Next, optimizing computational parallelism involves applying directives to allow operations to be implemented in parallel. This may involve unrolling and pipelining loops, or applying the data flow directive to implement task parallelism inside the kernel. Compute units can be optimized further by reviewing data widths and arithmetic functions on two levels. Data widths or data types should be reviewed and matched to higher level interfaces to maximize bandwidth. FPGAs are not restricted to standard data types and can implement custom precision arithmetic. Lower precision custom data types reduce on-chip and off-chip storage requirements and reduce the size of the data path operators we need. We can use system bandwidth more effectively if we only need to move these smaller data types, and we can save FPGA resources by using smaller operators. Finally, optimizing the memory architecture may involve things like array partitioning, again to try and map the architecture of your design to the data processing requirements. Array partitioning allows you to build custom local memory hierarchies inside your design. We'll examine each of these areas in the next slides. Some interface optimizations can be carried out by reviewing the architecture of your system and the higher level interfaces connected to a kernel. This may have been covered when optimizing host code, for example, deciding on the width of the interface. For reviewing interfaces in more detail, the kernel trace provides a graphical view of the data transactions in the design and their properties. We now want to consider the efficiency of the interface and perhaps review if the correct decision on interface type was made previously. For performance, maximizing the data throughput of the interface is now the main goal. For AXI ports that support burst transactions, we can review if bursts are actually being used and the efficiency of those transactions. Key metrics from the trace data will be the burst size, indicating how many bytes are transferred through an interface at a time, and the burst length. The length describes how many packets are being sent within one transaction. In this example, the burst length is 1 and only 4 bytes are being transferred for the highlighted transaction. The efficiency of this transaction is therefore fairly low. If a lot of data is to be transferred through this interface, or if we see a lot of similar transactions on this interface with low efficiency, the designer should investigate why the throughput is low and if the burst length and width can be increased. There are many examples of when bursts should be used. Accessing global memory from the kernel usually has a relatively large latency. Global memory transfers should be done in bursts where possible to reduce this latency overhead and improve the bandwidth usage and efficiency of the memory interface. This may also help other independent kernels that may also need to access the same memory bank. To infer the burst, the pipeline directive can be applied to loops that access data. This will allow a burst transaction. In the example code, a pipelined for loop is used to read data from the input memory interface. The coding style reads from the global memory bank in a burst. You may need to check that there isn't other code inside the loop that prevents full pipelining. For example, other code or data dependencies inside the loop might prevent data being read in bursts. Reading from memory can be implemented in a dedicated loop to stream data into a local memory if necessary before it's processed from another loop. The data width of an interface can be automatically configured by the Vitis compiler based on the data type of the kernel arguments. To maximize the data throughput, data types should be selected to map to the full data width on the interface that the kernel will connect to. For example, if connecting to a 512-bit wide memory interface, the kernel code should be modified to take advantage of this full data width. In the first example, a native C integer type is used, and the interface will default to 32 bits wide. This will limit the memory bandwidth that can be used by the kernel. In the second example, the arbitrary precision data type APUint is used and configured to be 32 bits wide to match the memory interface. The internal kernel code may now need to be updated to take advantage of this wider type. We saw the width of an interface can affect performance. The number of interface connections can also have an impact. By default, Vitis will generate a single AXI port per kernel. All arguments will pass through this interface. If different I/O processes within the kernel need to access the interface at the same time, there will be contention. Access to the interface will be sequential and may reduce the performance of your design. To address this, multiple AXI interfaces can be generated per argument by specifying a bundle name in a HLS interface pragma. In the example here, there are 3 large data interfaces. 2 inputs are labeled pixel and weights, and 1 output labeled out. These inputs and outputs connect to a global memory controller. By default, they will go through a single AXI interface. The bundle keyword in the HLS pragma defines the name of the AXI port. The system compiler will create a port for each unique bundle name. When the same bundle name is used for different interfaces, they will all be mapped to the same port. Sharing of ports helps save FPGA resources, but can limit the performance of the kernel. In the example here, 2 bundle names can be defined to create 2 distinct ports, gmem and gmem1. The kernel will access pixel and out data through the gmem port, while weights data will be accessed through the gmem1 port. As a result, the kernel will be able to make parallel accesses to pixel and weights, potentially improving the throughput of the kernel. The HLS interface pragma is used during Vitis compilation, resulting in a compiled kernel object, the .xo file, that has 2 separate AXI interfaces. During system compiler linking, the system interfaces can be mapped to specific global memory banks if required. Loops in the kernel code can be either pipelined or unrolled to take advantage of the parallel nature of the FPGA architecture. By default, loops are neither pipelined nor unrolled. Each iteration of the loop takes at least 1 clock cycle to execute in hardware. If the logic inside the loop is complex, each iteration may take longer than a clock cycle. The compiler can unroll a loop, either partially or completely, to perform multiple loop iterations in parallel. The designer can specify this using the HLS unroll pragma. In this example, by default, the design will take 4 clock cycles to execute the loop. By applying the unroll pragma, the design will take 1 clock cycle to complete all the loops. Unrolling loops can lead to a very fast design with significant parallelism. However, because all the operations of the loop are now executed in parallel, this requires more FPGA resources. Loop unrolling needs to be balanced against available resources in the target device. Generally, it's good practice to start unrolling loops that have a small loop body or a small number of iterations. For nested loops, you can start unrolling inner loops and work your way out. If fully unrolling a loop consumes too many resources, you can also partially unroll a loop. Another method of improving efficiency is through the pipelining of loops. By default, every iteration of a loop only starts when the previous iteration has finished. In the example shown here, a single iteration of the loop adds 2 variables and stores the result in a 3rd variable. Assume that in hardware, 1 iteration of this loop takes 3 clock cycles. Each operation, read, add, and write, takes 1 cycle. If the loop has 2 iterations, it will take 6 clock cycles in total to complete, as shown in the diagram. The throughput is 3. It takes 3 clock cycles to produce an output, and the loop latency is 6. If there were 100 iterations of the same loop, the throughput would still be 3, and it would take 300 clock cycles for the loop to complete. Pipelining a loop can be enabled by the pragma HLS pipeline. This means that subsequent iterations of the loop overlap and run concurrently as shown. In this example, the throughput is increased to 1. That is, data is processed on every clock cycle instead of every third clock cycle. The number of cycles it takes to start the next iteration of the loop is called the initiation interval, or the II, represented by 2 capital letter I's. In the first case, the II was 3, meaning each successive iteration of the loop starts every 3 cycles. An II of 1 is the ideal case, where each iteration of a loop starts in the next clock cycle. When you use the Pragma HLS pipeline, you can specify a target. By default, the compiler always tries to achieve the optimal II equals 1. Note that pipelining will automatically apply unrolling to the loop. Pipelining can also be applied at the function level rather than only inside a loop. Here you can see a simple example demonstrating the behavior of function pipelining. Pipelining at this level starts the next iteration of a loop immediately. Loop pipelining within the loop only pipelines iterations inside that loop, as we saw previously. If a loop is called multiple times, it will only restart after the completion of the total loop iterations. This will also apply to other functions at this level of hierarchy. Pipelining at the function level will also pipeline all functions and loops in the hierarchy below. Data flow is conceptually similar to pipelining, but is applied to function bodies. Multiple functions can run concurrently, and this is known as task-level parallelism. In the example shown here, the default behavior is to execute and complete function A, then B, and then finally C. With the data flow directive applied, the compiler can schedule each function to execute as soon as data is available. This would also apply to loops at the same level of hierarchy. In this example, the original top function has a latency and interval of 8 clock cycles. With the data flow optimization, the interval is reduced to only 3 clock cycles and a latency of 5. By default, the Vitis compiler maps large arrays to on-chip memories on the programmable logic. Memories store data efficiently, but with limited access ports, they can limit the performance of the application, the memory bandwidth. All the elements of an array can't be accessed in parallel when implemented in a memory. Depending on the performance requirements, you may need to access more elements of an array than a single on-chip memory block allows. The Pragma HLS array partition can be used to instruct the compiler to split the elements of an array and map it to smaller arrays or multiple memory blocks, or even to individual registers in the FPGA if you do need to access all elements simultaneously. Note that the default behavior of allocating memories will be the most efficient in terms of FPGA resources. Partitioning arrays for increased access comes at a cost. A block RAM is one type of on-chip memory and is 36 kilobits in size. If we have an array that fits perfectly in this block, but we need to access twice as many elements of this array as one block RAM supports, we could use 2 of these blocks. This will give us twice the bandwidth, but we're doubling the memory resources we need for this type of architecture. You should understand the access pattern of your array, that is, how many elements of your algorithm that you need to access at a time, and also the order in which you need to access those elements. There are 3 types of memory partitioning in Vitis. With block partitioning, the original array is split into equally sized blocks of consecutive elements of the original array. As an example, if we have an array with 100 elements, the block partition by 2 will take the first 50 elements and assign to one memory, and the next 50 elements to another memory. Partitioning by 4 would do the same in blocks of 25 sequential elements. With cyclic partitioning, elements of the original array are interleaved. For example, again with 100 elements, cyclic partitioning by 2 would still split into 2 blocks of 50 elements, but this time all the odd indexed elements would go into one memory and the even elements into another. That is 0, 2, 4, 6, 8, etc. will go to one memory and 1, 3, 5, 7, 9, etc. go to the other. This method of partitioning is useful when the algorithm accesses elements sequentially. The block and cyclic partitioning factor can be increased to subdivide arrays into smaller parts. Complete partitioning is when the array is split into its individual elements. This corresponds to resolving a memory into individual registers inside the FPGA. This can split an array up to give an algorithm access to all elements in parallel, but for large arrays, this can consume a huge amount of FPGA logic.